Diffraction is, it's real simple. What diffraction is, notice, here we're going to the minimums, the angle we're going to get is the minimums, but it's basically if I have a real, it's as light goes through there, it kind of bends out like this, okay? Now then, the longer the wavelength of something, the more it bends when it goes through an opening. Like sound has a really long wavelength, very, very long wavelength, and it bends. Radio waves, AM, FM radio waves, have very long wavelengths, so therefore, when they encounter an opening or a slit or something, they bend easily around it, all right? But light, on the other hand, visible light has a very, very dinky wavelength. And it's, an analogy that I can make is, again, a piece of rebar or something like that in the street. Okay, it bends real easy if it's really, really long, but get a piece of rebar this long and try and bend it. All right, it's hard. You can't do it. All right, it gets very hard. All right, and light's the same way. So it doesn't bend. So someone standing just on the other side of this door at a 90-degree angle can't see my reflection. They can hear my voice because the sound waves are really long and they bend around that way. But the light waves don't bend so much. All right, and so we're just looking at basically diffraction means bending. That's it. It just means flowing out. And things that are waves, things that behave like waves, flow out, and when they go through an opening, they kind of branch out like this. Okay? All right. And so this is basically the single slit argument for diffraction. And because light waves diffract, a classic example of the diffraction of a light wave actually bending around something, though it will bend around something, just not near as much as other things, is if you take a flashlight and you shine and you put like a circular thing in front of the flashlight, what's the flashlight do? It kind of forms rings on the wall and there's actually a bright center. And you're like, well, where the heck did that come from? You would think, now if light behaved completely like particles, all the light that was hitting that little circular disc that you had would just bounce there and not go anywhere, and then the other light, and so you'd have a dark center and a bright ring. But actually with diffraction, you've got something completely different. You've got a bright center because it actually went and bent around that little disc. You've got a bright center, and then you've got dark fringes and rings that come out like that. So, which is basically this. It looks like this. It's just the opposite. It'd be if I smashed all this down here and hit it, and it bent around here, and then it would form a bright center and then go like that. Okay. Now the equation for that is pretty straightforward. The condition. Now notice, diffraction minima. When we talked about this on Monday, when we say minima, what kind of interference are we talking about? Destructive, right. In other words, we can't see it. Okay, so go back real quick to the picture. See, the angle goes from the center bright fringe to the M2. Right here is the second dark fringe, okay? And so the equation is pretty straightforward, where this W is the width of the slit, the sine of the angle that the dark fringe 1, 2, or 3 makes. Notice they don't have m equals 0 because m equals 0 is a bright fringe, all right? And the diffraction pattern will be wider for longer wavelengths and narrower slits, okay? In other words, if I narrow the slit, it's going to go like, it's going to just like squeeze it, type thing. So it'll kind of spread out like that, okay? And the central maximum is twice as wide as the side maxima, okay? And its width is, because of the small angle theorem, basically this L over Y, they kind of are getting this from the L over Y. Y is, let me go back real quick. Here's your distance Y. It goes from here up to here. That's your distance Y that they're talking about. Okay. All right. So All right. And so the maximum thing is twice as tall as the 1. All right. There we go. Now, if we do a diffraction grating is a series of small slits with a uniform spacing. All right. Basically, it's like a CD player, but remember that's reflection type grating. But we use diffraction grating. One of the things we use diffraction grating for is in spectroscopy. All right. Because it breaks things down into its different. Now notice we're talking about we've got ends now, the different ends. In other words, when we use a diffraction grating, what we're going to come up with is we're going to have the spectra here, spectra here, up to a certain maximum. All right, up to a certain maximum depending on the grating. All right. Double slit interference, single, and then here's the combined diffraction grating that you're going to get. And it's a way to use spectroscopy type things. Here we go. Here's what I mean. Okay, when n equals 0, you're getting all this white light coming in here. Then when n equals 1, we've got the spectrum here. Now this is a prism. This is what we used to use. This is a prism, and a prism wasn't a very good idea. One, because you had to know down to, it wasn't as accurate as using a diffraction grating type thing, because one, the prism, it threw things off because you had to worry about the index of refraction of the actual prism and stuff like that. But with this one, you can put things in like a vacuum type thing and get a good spectral analysis of how the light is behaving on that, and get the different visible wavelengths, so you know which material you're looking at. All right. Okay. All right. But it breaks it down the same way. So diffraction grating in a thing. This is for constructive interference. That's not what I was wanting to get to. Nor that. We'll talk about polarization in a minute. Let's do an example of diffraction grating here real quick. All right. Okay. Here's an example of one. It says a particular diffraction grating produces n equals 2 spectral. All right, so what we're looking at here is, let me go to the dot cam here real quick. And like I've said before, and I'll say it again, getting ready for your last test. Let's zoom in a little bit. Please read. First of all, do the homework. Some of you found out that once you did the homework, you were like, darn, I wish I'd have done the homework before that one test, and then I'd have aced it. I'd have aced that test because it's just like kind of like the homework. The other thing, too, that will help you, dang, the mosquitoes are already out. But anyway, the other thing that will help you, too, is if you do these, now study, I'm going to tell you that the way to study physics is the same way you kind of studied math, all right? Not the way you study psychology or biology. There's two different ways that you study for things. I know more about studying for psychology because that's where my doctorate work is, in education. So we do a lot of psychology type stuff. And a lot of that is just memorizing a bunch of terms and going, okay, I think I know what this means. And so if this happens, all right, I got this. Whereas physics is more, there's like 4 or 5 big ideas that are being thrown at you. And then you've got to be able to read the problem and do it. And the best way to study it is to go through the examples. Don't just read them, but actually sit down with a sheet of paper and pretend like you're going to have to get up and teach each one of those examples that they have in the book. And if you go through it and actually write it down, now I've got it. Whereas if you just try and memorize a bunch of formula, or you go, oh, I don't have to memorize anything because he's allowing me to bring in the formula sheet, I can bite you, because you might not know how to actually read the problem. So we're going to look at a diffraction grating problem here, because these slides don't help much. All right, so here we go. Here's the big idea. It says a particular diffraction grating produces n equals 2 spectral. So it's got n equals 2 spectrum, spectral order, at an angle of 32 degrees. So theta equals 32 degrees.
You're light-heavy.
Yeah. So angle, so equals 32 degrees. For a wavelength, lambda equals 500 nanometers. So far, I don't have to convert anything. But then it says, the first question is, and this is what I think is kind of cool about this, it says, how many lines per centimeter does the grating have? In other words, how many small, dinky little slits per centimeter does the diffraction grating have? And the way we find that is D is equal to 1 over N, where N is the number of lines. Okay? Number of lines in the gradient per centimeter. That's the number of lines per centimeter in the gradient. So you're like, well, wait a minute. Give me a formula. All right, here's the formula for diffraction grating. It's D sine of theta equals N times lambda for your spectral order. Okay? All right, so they gave us everything we need. They gave us everything we need, except that we need, number of lines per centimeter. Sorry. This is on page 825. 825. All right. So I'm going, okay. All right. So I need to find D. Once I find D, I can just flip it over and take the inverse of it and get the number of lines per centimeter on this thing. So let's solve for D. First of all, I got to change lambda. Since D is going to be in centimeters, I got to change lambda to centimeters. And so that's it. Since it's in nanometers, that would be, here's what I'm going to do. D times the sine of 32 equals 2, because we're looking at the second spectral thing. In other words, think of the prism, and we're looking at the different spectral things that are showing up there. All right. After we get to 1, then there's the second one, and we're going to see how big this is going out. So N equals 32, 2 times lambda, which would be 500, times 10 to the negative 7 centimeters. Okay, it'd be 10 to the negative 9 if it was meters, but it's 10 to the negative 7 since it's centimeters. So I say D is equal to 2 times 500 times 10 to the negative 7 centimeters divided by the sine of 32. And that comes out to be kind of a small number. Comes out to be 1.89 times 10 to the negative 4 centimeters, which equals 1 over n, which actually equals 1 over n. So if I want to change it, so if I want to get the number of lines per centimeter on this diffraction grating, have this, then I hit my good old x to the negative 1 key. That's my savior key for me all the time. Instead of just going 1 divided by that. And then I get, that comes out to be about 5,300. So that's 5,300 lines per centimeter. Okay? All right, that's the first question. All right, now the second question is, at what angle, if n equals 3, what angle will it be? Well, that's pretty straightforward. All they wanted us to do is change n to 3, and so that's easy to fix. We can do that all day long. Just do this. Say, all right, remember, here's what we're doing. Here's your big formula for diffraction grating. And remember, diffraction grating just means how far it's getting spread out. Diffraction grating. Okay, so I get, what do we say? D sine theta is equal to n times lambda. All right, so I'm going to use the D that I had before. Use the same D because they want us to know what we're going to do now is we're going to change n to equal 3. Okay, and use the same D, but now theta is going to change. So I wind up with this. the sine of theta is equal to n lambda over d. Now again, you have to change everything. Whoa, boy, we just got stuff to smack. It's like a little poltergeist physics room here. Anyway, it's not liking what's going on. I don't know if you can do anything about that. Well, I don't want people to get hot, though. So I think it'll be all right if we raise the blinds a little bit. It won't affect the crazies over here. All right. Okay. Anyway. All right. So then theta just equals. There we go. The inverse sine of that. Oh, where n equals 3. And you just plug that in and you get the number. Now then, it says, what is theta max? Or what's n max? The maximum number of different spectral things that we're going to get. Think of the prism again. Remember, it had 1, 2. This one we did for 3. And will it do 4? To find n max, that's pretty straightforward. There's nothing much to that. Here's how you find n max. It's real easy. You just do this. N max is less than or equal to d over lambda. Now, why is it d over lambda? Because the sine of theta, because we've got, did I say d over lambda? Yeah. That's right. Because it's at a max when sine theta is equal to 90 degrees. Okay? Or that's just right at the maximum. So when theta is 90 degrees, what does that equal? 1. So to solve for n, if this is 1, you just take d over lambda. That's why that's so straight. So when we do this, though, for this one, when we get the n max for this problem we're doing here, we find out that that's 3.77. So if it's 3.77, what do you think it's saying that, hey, you can see the third order spectral thing, but what about the fourth? No, right, good. So the max that it can be, n max equals 3 is visible, equals 4, not visible. Okay? All right. That's all you need to know pretty much about diffraction grading. Actually, you just need enough to do your homework problem if there was one on it at all. But I needed to show it to you because you won't be tested on that. Now, Brewster's angle, you might be tested on. Oh, we got to do polarization. Then we'll do Brewster's angle. I keep getting ahead of myself here. All right, now, polarization is kind of a cool thing. Let's go back to the slides here. Hopefully they've got better slides for polarization. Yeah, here we go. Now then, here's basically unpolarized light. All right. Here's what they're saying here. Well, if I got unpolarized light that's coming at you, all right, unpolarized light that's coming at you, remember, you've got that electromagnetic, you've got that electric field going in all different directions. Okay? It's coming in all different directions. But if it's going this way, it's got a lot of it's going up and down like this, and then this is the part that's going in and out. Okay, these are the parts that are going in and out. All right, so that's when it's unpolarized. If I partially polarize it, that means I'm being partial to the. I don't mean partially and partially. That means if I partially polarize it, then there's a lot more of just the straight up and down waves coming at me than are traveling this way than the ones that are coming in and out like this. All right? And then if I linearly polarize it, basically what I'm getting is just this amount of the electromagnetic waves, the ones that are going straight up and down. Okay? So when it's going, so how many of the electromagnetic waves, the intensity, how much of the intensity is left if it's totally polarized from this picture to this picture? Right, exactly, half. Good. Good. All right. So anyway, so this is what it's saying. So this is the big idea here. I like this stuff, so I get all excited. I start throwing things. All right. But anyway, because it's kind of cool. Now you just got to keep in your mind. You're going, wait a minute. There's infinite number of lines, right? I know what some of you are thinking. You're going, wait a minute. How can you just blanket say that half of it gets through? Because I can blanket say half of it gets through, okay? And that's why, all right? And we'll just leave it at that for right now. But I think this illustration shows pretty well because these guys going up and down here, we're adding them all together. We've even got the ones that are all right. So these guys going like this are getting polarized out. But this one, like this, the only part that's coming out is its y component. All right? And so we take all the y, this means all the y components. This means all the y components, all the y components. All right, so now we got a lot more y components. Now it's all y components. We've completely eliminated the x component of the thing, so therefore it's half. Okay? All right, because this line doesn't represent just this. Remember, the E field is a vector. This line doesn't just represent the one that happens to just be on that slit. It's all the y components that got through, because they were able. The y component of each of these guys, the y component of each of these guys was able to get through. The x component's got eliminated, so therefore it's half. Is that a good qualitative enough explanation? Yeah. That's the best I got. So that's the best I can do. And that's the best I've ever done, actually. Usually I just say, just trust me. It's half. So anyway, okay. So here's what we got. Unpolarized, the electric fields have random directions. In partially polarized light, the electric fields are clustered around a preferred orientation. Fully polarized light, the electric fields are all in the same direction. So we just get the y component, or we just get the x, depending on how we want to, or we just get the x component, or we get the 45-degree component, okay? But it'll always just be half, no matter how we do it, which is kind of, it's something to mull. You know, sometimes in physics you just got to go, I'm going to mull this for a while. I think I like biology better. But anyway, in a fully polarized light, the electric fields are in the same direction. So how do we do the problems then? What are we going to expect? All right, here is the classic problem. Now, notice, light source coming in, hits a polarizer. Certain materials have certain polarizing ability, okay? And that's a whole field in optics and material science and solid state physics and all that is coming up with good polarizers and stuff and analyzers and things so that you can transmit light well and get good pictures and all kinds of stuff. But anyway, all right. So here's your intensity. I naught coming through. Now, one thing that I've noticed since I switched physics books, it was pointed out to me about 2 or 3 weeks ago when you guys were doing the lab on intensity. You had the little magnifying glass and all that kind of stuff. This book doesn't talk about intensity of light. Doesn't give you the equation for it. I forgot what it was. So, but anyway, sorry. Hopefully it's in your lab manual. And I know that was written very clearly and you understood it perfectly after reading it once from the lab manual. So, anyway. All right. Anyway, so it goes through the polarizer, so I wind up with half the intensity, okay? And if the next analyzer, notice, if the next analyzer is oriented just like this polarizer, then it still is just going to, what's going to come out of there is a half. Now then, the other thing that happens, but notice, if I take a polarizer and I take an analyzer of the same material, it's just that the first thing to hit it we call the polarizer. The second thing is the analyzer. The third thing's the analyzer. The fourth thing's the analyzer, okay? That's just the way we talk in optics, all right? And then if I orient this thing at 90 degrees, look what happens. It's going to take away, this is going to just give me what? The ones going this way. But if they've already been taken out, what happens at this end? No light gets out. And I hope they had the good picture from the book. Oh, of course not. There's a good picture to show. All right, in your textbook. Oh, I can do it. I can do it this way. We don't need no stinking slideshow. We can do it this way. Right here. Here's some polarized glasses, okay? And notice this is the first polarizer. Then when we put the next polarizer on there and we orient it at 90 degrees, what happens? Can't see through it at all, okay? Nothing gets out. All right, so that's kind of a cool little thing. But anyway, all right, so now let's figure out how to do one of the problems. So what do the problems look like? Did I assign a problem with polarization in the thing? Oh, I didn't? Oh, darn. Okay, but you guys get, if there wasn't one assigned, then I'm not going to test you over it, so we'll just move on. Okay? So we'll just move on. All right. All right. So here, notice they put the second polarizer, second analyzer in here, and now here's kind of a good question. Okay, if we remove this guy, hold on a second. Notice comes through here. This goes like this. Nothing gets out. But let's say we put another thing in here that orients the light a little bit differently. It says, okay, we're going to orient this thing so we're going to get a little bit more light out of there. See, since this one's not oriented at 90 degrees, something's going to get out of there. And what's going to get out of there is going to be 1/2 the cosine squared of this angle difference between the straight up and down and now that it's curved like that. This is called, I don't know how to pronounce it. I don't know French. I've heard it all different ways, from Mal's to Malus to May's law. It's M-A-L-U-S. Anybody know French? I think I've asked that before. M-A-L-U-S. Malus law, Malus's law. I got to look it up because I know Malus isn't right. Malice. With malice towards none, we'll move on. But anyway, so anyway, it comes out at this orientation at 1/2 cosine squared of theta. And then it would come out, so then this becomes your new I, and then when it comes out of this one, it would be this, it'd be I to the 1/2 cosine squared theta times cosine squared of 90 minus theta. Oh, they got it right here. Okay, good. That would be the intensity of the light coming out of there. So I can reduce the intensity, but still some light's going to come out. All right, good. There we go. Now, Brewster's law, polarization. Basically, to totally polarize my light, all right, I've got a light ray coming in, unpolarized light, partially polarized, all right, when it reflects back, because the intensity is lost. There's some intensity lost. Now, our human eye can't detect it. Human eye really can't detect polarization, all right? We can detect things that are heavily polarized when they really lose a lot of intensity, but we can't detect the first polarization. Can't see that too much. But when it's linearly polarized light, in other words, notice, I've gotten rid of all the y part of that thing, and it's all nothing left but the x orientation here, all right? When it's linearly polarized, what happens is my angle of refraction, actually my angle of incidence and this, my ray of diffraction, my reflection ray, my ray of refraction actually add up to 90 degrees. Okay, they form a 90-degree angle with each other. So how do we find out? The unpolarized light? Okay, bear with me. I'm going to do something scary. I'm going to derive an equation, but it's fairly straightforward, and it's based on Snell's law. Oh, and by the way, this gets polarized because this penetrates in, so it doesn't. What's reflected out, the intensity of what's reflected out, is not near as intense as this because some of it goes in here. Conservation of energy still applies even to light. Okay. All right. So here we go. Now, so let's try and figure this out. All right. I'm going to draw this. Here's my ray coming in here. All right. Here's my theta p. Can you see what I'm doing? Yeah. Theta p. All right. And then This is going to reflect out here. What's that angle going to be? Theta p, right? It's going to be theta p. I'm calling it theta p for polarization. Theta of polarization, okay? All right. Now then, it's going to bend here. Now the thing I can't use is good old, even though I've almost drawn it this way, I can't use good old, what do you call those? Alternate angle theorem type things. Can't use that. But here's my theta of reflection. And I want this to be 90 degrees. This has to be 90 degrees. So, here's what we've got. Now look, this theta p occupies this right here. This is 90 degrees. So what's this angle? Yeah, it's 90 minus theta p, right? 90 minus theta p. And so if this is a 90 degree angle, so if this is 90 minus theta p, what's this angle right here? Yeah, it'd be theta p, right. This is theta p. Ha ha. So theta p plus theta r adds up to what? 90. Exactly. And so what's theta r equal? 45. No, not, well, it could if theta p was 45. Yeah, probably. All right, but anyway, so theta p equals, so this equals theta r. So now, let's apply Snell's law, where we've got N1 sine of theta p, well, equals N2 sine of theta r. But I know that theta r, this is one of the few derivations I've made you sit through just because the old trig teacher here just kind of likes this one. All right, 90 minus theta p. What's the sine of 90 minus an angle? What's the trig identity for 90 minus sine of 90 minus an angle? The cosine of 30 is equal to the sine of 60, right? Cosine of 30 is equal to sine of 60. So this would just be the cosine of theta p. All right? We're getting somewhere now. Trust me, we're getting there. And sine of theta p equals N2 cosine of theta p. All right. So now, sine of theta p over cosine of theta p equals N2 over N1. What's the sine over the cosine? What trig identity is that? Tangent. Right. So that's why in your book, the tangent of the theta, the angle of polarization is equal to N2 over N1. And that's called Brewster's angle. So they say that Brewster's angle, theta b, is equal to the inverse tangent of N2 over N1. All right. Bear with me real quick. Now that we know, and that's the angle that we'll shine that in so that it will, it'll be polarized. It'll linearly polarize the light. The reflection will be polarized. All right, so now let's take a look real quick because whoops, do we need to go back? There you go. All right. That's what I like about doing it. Of course, some of you others go, wait a minute, I needed it too. Oh, well, we'll put it up there in a minute. All right, now, it's also in the book. But anyway, let's do this. One of your homework questions. Now, you're going to have to bear with me here for a second because I'm going to have to go here and call this up. Go to good old mastering physics here. Whoops, that's not me. I always do this wrong because this is not, it's actually this. let's do your Brewster angle problem that's in your thing. Now you might see Brewster, just because I like it. I think Brewster's angle is kind of cool. All right, and I'm kind of dismayed that I didn't assign a intensity a different polarization problem. Courses, who are you guys? 220A spring semester. And this is from what? 24 and 25? Is it 52, this one? Hey, wait, I had a polarization Malice's law in there. He's fair game. We might go back and look at that one too. All right, anyway, here we go. Assume all angles to be abstract. No, exact. Okay. All angles are to be, okay. All right. Well, it is. It has congruency and all that. That's abstract thinking. That's why there's a theory out there. All right, a little bit of educational theory thrown at you. How many of you took, because I know I'm dealing with some of the best and brightest when you were in high school, how many of you took algebra when you were in 8th grade? Right, that's what I thought. Most of you took algebra in 8th grade. Then how many, now young ladies, don't be embarrassed by this, but how many of you then, when they thrust you into geometry, you hated it with every passion of your being because you weren't, all right, right, exactly. Now one of the things is because you're too young. You're too young for geometry. It's an R-rated subject. But anyway, well, my daughter did the same thing. She was very good at algebra, because the way they teach 8th grade algebra is very algorithmic. You do this, you do the steps. Everybody likes that. 8th graders, they can eat that up, right? But then you get into geometry and you got to, 2-column proofs and all this kind of stuff, and you hated it. And basically what they've done now is they've turned all the geometry text basically into an algebra text anyway. So, but which I don't like either. But what happens is your brain's not developed enough. Your little cortex, your little thing, you guys know more about this than I do because you've taken all of this anatomy and stuff. But anyway, that little stem that combines your left and right hemisphere isn't quite developed until you're 16 or 17. For most people. Some people it develops a little earlier, some people later. Some people never get geometry ever. But anyway, and until that's developed, it's really hard to go from concrete to abstract and put them together. And so geometry becomes difficult. So that's why I think, biologically we're damaging children by doing algebra too fast. I mean, what's the rush? You got it. What's the rush? Take algebra when you're a freshman, but oh well. Gifted education is the little league of education anyway. Why isn't my child gifted? Because they're average. Anyway, sorry, and that's okay. That's fine. All right, but anyway, sorry. Okay, but so and so has terrible grades and they're in the gifted program, right? Because school bores the hell out of them, so we got to do something with it. But anyway. All right, so it says, what is the polarizing Brewster angle for light externally incident on the same boundary? Okay, the critical angle, this is good. So critical angle, what does we're going to assume, we're also going to have to assume what? That we're doing air, all right? That N1 is equal to 1.00. Now, to do this problem though, so they gave us the critical angle. And what do we have to do with that critical angle? I wish I had one of those whiteboards like they've got at Penn Valley where you can actually just write right here. And it turns out really cool. And then you hit save, and then you all could go and upload it on your own computer. It's really, the junior colleges are kicking our butts as far as technology in the classroom goes, but that's okay. They get more money from the state. But the critical angle for total internal reflection in a certain media boundary is 43. So here we go. So what is this going to tell us? What are we going to be able to get from, what information are we going to get from this? What? We're going to find exactly. We're going to find the ratio of N1 to N2. We're going to find the N2, we're going to find out what N2 is here. Because we've got the sine theta c, now this was a test question, equals N2 over N1, right? Mystery problem. There you go. Isn't this the idea behind the critical angle? Wrong. I've got this wrong. It should be N1 over N2. Okay? N1 over N2. Where, remember, the critical angle we're dealing with, this is the N of the substance. So let me write it this way. N of substance, no, N of air over N of the substance. Because what happens if I have that that N2 is greater than N1? What happens? Yeah, it's not going to work. It's not going to work. Okay? Oh! Gosh dang it. This is confusing. Let me try this again. Sorry, Homer showed up there for a minute. Sine of theta c. Okay, now, here's what I'm sorry, I have to do it this way. I have to do it, okay, if I happen to be in the substance down here.
Is N2 over N2.
Right, right. Where, see, this is N1 of the substance, and this is N2 of the air. So I've written it the same way. So I've got it right. I've got it right. Okay, good. Whew. All right, so the sine of the critical angle equals N over the air divided by N of the substance, which is going to be N of the substance, N of the substance is going to equal 1.00 over the sine of 43. Okay? And so, substance. I must be hungry. Substance. There we go. All right, so now, take 1 divided by sine 43. Hopefully this isn't on radians. It's on radians. No, it's right. 1.47. So now we'll just call this 1.47. And so now, Brewster's angle says this. Tangent of theta b equals 1.00 over 1.47. And theta b should be the inverse tangent of 1.00 over 1.47. Right? What? No, I changed it just because I was getting ready to do Snell's law, but I decided not to. All right, so I just jumped in. Oh, so let's see if this is right. So we do the, so hold on, hit 1 over. Oh, second, I'm going to see if I can do this in one fell swoop. Inverse. 34.3 or 34.2.
Don't you have to do 90 minus 34?
Let's go and find out. It says, what is the polarized? No, I think that should do it. Let's see. Let me try, because you guys are going, we tried this and it didn't work. All right, so let me see. 34.3. Here we go. 34.3. Drum roll, please. Submit. Try again. All right. So try 34. Try again. Okay. I've ignored Cody before at my own peril, but I'm going to listen to her this time, because what she's saying is, hey, dummy, you're looking for the theta p, not the Brewster's angle. Not the Brewster's angle gives you, yeah, I thought that was theta p, right?
No, it works if you subtract.
Oh, okay.
You told us at the very beginning.
What's that? Oh, okay. Okay. Right. I had it inversed. I had it reversed. Okay. So like I said, ignore Cody at your own peril. But anyway, so here we go. 90 minus 34. You better be right now. Yeah. There we go. Whew. So Kenyon caught me. He said, wait a minute. Your Brewster's angle thing was wrong. Because that's what somebody over here was trying to say. They're saying, wait a minute. N2, are you sure? Yes. I'm going full speed ahead. And when I get try again, that means I get to try again and go 90 minus. All right. There we go. Okay, I think that's enough. I think I've done enough damage today. I was going to try and get through 25 today. That was silly.